Hey everyone, my name is Rudy Hill, and I've been working as a FPGA engineer for the last 5 years. And today we are going to be talking about CMOS circuits and end with an example of an inverter circuit. So the very basic thing that you need to know is just basic resistor circuits, not even capacitor and inductor stuff. So basically just physics two type stuff, basic circuits class stuff, and basic logic, and if you've kind of seen that, like what's an and, what's an or, that sort of thing. What's a not? So basically, an inverter circuit's going to be a not, but we'll get to that later. Um, so this is for anyone that's kind of doing a class, any student that's doing a class on these types of circuits. This is for a very basic understanding, not going through the semiconductor physics and all that. Um, but we'll just start off and talk about a MOSFET. So it's a metal oxide semiconductor field effect transistor. That's a mouthful, but the bottom line is that the metal oxide semiconductor part of MOSFET refers to the actual material. So I think there's other ways to construct transistors, but this is definitely the most common of when you hear about chips being made and transistors. This is kind of what we're talking about here. Field effect transistor, that has to do with the actual way that the gates are turned on and off, and we'll talk about that in a little bit, anyways. And basically, NMOS and PMOS are just the different kinds of types, and we'll talk about that once again. But um, the NMOS and PMOS are named after the actual configuration of P-type and N-type material. Which you could look further, and I'll probably make a video at some point kind of discussing some of that chemistry a little bit, some of that physics about how do you actually get a semiconductor which normally doesn't conduct to conduct, has to do with holes and uh, free electrons and that sort of thing. But that's not what we're here for. We're here for computer engineers that just want to have a basic understanding of how to use a transistor to build circuits. So we're going to build a very basic one. So in physics one, you may have been familiar with gates. Basically, you would have some sort of voltage source and some sort of resistor capacitor or something like that. It's like, okay, once we turn it on, like what's the voltage across this and that sort of thing. So, I'm kind of assuming that you has a basic circuits one, or physics two kind of knowledge of circuits, not anything too deep, but you just have to know a switch basically. But if you think about a manual switch, kind of the way I've drawn it, this is the open, and this is a closed switch. And you would think about that, you would actually have a manual switch that you put down, kind of like in a dramatic Frankenstein style, where you're pulling down the switch or something like that, or just a switch in your house. But basically, it's a manual switch, so you're taking mechanical slash kinetic energy, and you're closing the circuit, and now okay, the gate is open, and now electricity can flow. So that's what this stands for. G for gate, and we'll discuss this later. But D for drain, S for source, and these are the two positions here, right? So we have an open circuit and we have a closed circuit. So we're not doing anything crazy yet. But what we are adding, kind of for some basic definitions and basic mechanics, is I'm drawing the N-type MOS uh, MOSFET here. So basically, it's denoted like this. It's kind of like a capacitor here, I don't know, something like that, because there is a capacitive effect. Again, we're not going to talk about the physics today, but just know that that it is supposed to look like a capacitor because it's related. And we'll denote this, the drain. We'll label it, I guess. Uh, let's get some better handwriting here. Drain. Source. And then we'll call this gate. So gate for obvious reasons, kind of the example before. So there is a direct analog of what I was drawing here of a basic switch to this NMOS. So pretty much you apply voltage. So there's a drain voltage. This is usually positive, and this source is usually negative. That always confused me because like, okay, so current is depicted as flowing this way, and it always confused me because it's like, okay, well, if why is this source is usually connected to ground and drain is usually at VDD or something. Yeah, why is it going down? Like, why is it called source if the current's going that way? Just recall for a second that current is the opposite of where the electrons are actually going. So I like to think about a source like it's a source of electrons. Not sure if that's the reason, but usually this is the denotation here. There's other ways that these things are actually connected. So just understand that this is usually how it's drawn here. And the opposite of this is going to be a PMOS. Same thing here, drain, source, and here's the gate. And we know it's a PMOS because we're putting this dot. So I'll kind of discuss how they work. So with a with an NMOS, we'll label it here, NMOS and then PMOS. With an NMOS, you apply voltage here, and it allows current to go. Oops, that's not what I want. It allows current to flow. Um, with this, and we'll kind of just denote this, assuming that there's voltage on the gate, but we'll say that this I equals 0. I'll kind of draw this better out here, but basically, once you apply a voltage to the gate, it allows current to flow for the NMOS. Oops. And for the PMOS, you apply voltage to the gate, and it actually stops current. And it's the opposite. So in the case of an NMOS, if you do not apply voltage, current goes to 0. And in the case of PMOS, if you do not apply voltage, the current flows. So there's kind of specifics of how much current is allowed and all that sort of thing. But that's very basic. We're talking about this from a digital designer's point of view of um, what goes where, like which one is it? Maybe this is why you're studying of like, oh, which one is it? So that's kind of what it is. So I'll kind of denote it here actually to say that this open circuit. Um, so for an NMOS, this open circuit has to do when we'll say when the voltage on the gate is 1. We'll say it's a logical 1, so that's whatever it is. So there's like a threshold voltage. So that's what I'm saying. You kind of need to know some basic Boolean, but we'll just say basically it's on. 1 is on. So maybe if you don't know, could have known it. 1 is on, 0 is off. And this is like a logical one, so that this could be like some sort of volt. So really, what I'm saying, if you don't know, if you already know this, then you already know this. But if you don't, a logical one would be some sort of predetermined value. So in this case, I claim that this was VDD or something like that, the drain voltage. And so we'll say that when V gate basically is on, uh, we'll say we'll actually move this because we're saying that for the NMOS, it allows current to flow. So this is I equals big I. We'll call it that. And then I equals 0 here, right? So basically, when the gate voltage is 0, there's no current. When the gate voltage is 1, or VGS, but we'll call it a logical one. The current flows, and it's the opposite for PMOS. So in other words, for the PMOS, when the gate is on, when you apply a voltage here to the gate, it's gonna close the circuit and there's gonna be no current. But when you put no voltage, it actually allows the current to flow. So, hopefully that's clear. I might do a revision at some point, kind of make this more clear. There's many ways to think about it. This is kind of very basic concept is which one does which, and there's actual physics to it. Um, but now that we have that concept, we're going to actually use this for an inverter circuit. Um, so there's many other circuits you could do. Maybe we'll do later in another video. Ands and ORs and uh, NANDs and NORs and XORs and XNORs and there's a lot of fun stuff. And again, I'm assuming that you have basic Boolean algebra and maybe you're making that connection of, oh yeah, like I know those. Okay, so that's how you kind of build up circuits from like logic. But this is all like you're trying to just build a circuit from to transistors themselves. So the one thing I did not write here, which I should have, but I'll write it now, is a CMOS. So it's a comple complementary um, MOS, metal oxide semiconductor. Why is it called complementary? So we'll answer that with this example of an inverter. And I'll just kind of draw it. So let's just say here we have VDD. So here's ground. Maybe I'll do it more like this actually. But that's ground, okay? So the only thing I would put here actually is this. Oops, just kidding. So the question is, once we put power, uh, what's this gonna look like? What is what is the logic table for something like this? So maybe you want to think about it, and I can give you a second to think about that. But we'll just kind of continue. What we got to assume you pause the video and kind of worked it out. So we'll just kind of go through. So let's just say Vn. So like really, this logical one would be like a VGS, but we'll just use Boolean logic because it makes it simple. So you can kind of think about whatever you want. Actually, maybe we'll use VGS. Actually, maybe not. Let's make it simpler because there's complications and I don't want to oversimplify some stuff. So I'm kind of using voltages and logic interchangeably, but as an engineer, that's kind of what you want to do as a digital designer. Unless you're getting to the analog of it, it's not really helpful. So instead, we'll just actually relabel this as A, and we'll relabel this out as C. Actually, better letters. We'll say that this is X, and this is Y. Who knows if it's much better, but here we go. So if we say that X is 0, so what's that going to do? 0 is going to um, invert. So this is going to do the opposite. So this is going to allow current to flow, right? And then a 0 here. Okay, well, that's just going to block it, right? So clearly the current is going to come out here, right? This will be connected and this V out will be VDD, right? Again, not exactly. There are some resistances and that sort of thing. So maybe I'll kind of draw it differently. VN, V out, depending on how you want to see it, but we'll say that V in is 0 volts, then V out is going to be VDD, right? Or in other words, it's a 1. Now let's imagine it another way. Let's say that's a 1. So we say that X is 1, or Vn, let's just say, is uh, VGS. So it's like this threshold gate voltage or something like that. So let's imagine that's a 1. What is this going to do? This is going to allow current to flow, right? This is going to open up that gate. And what's a 1 going to do over here? Well, it's actually going to block it. So this is going to be blocked here. So these two will be connected here from ground to V out, right? So what does that mean? 0 volts. This is a logical 0. So you have, through this, have built your first inverter circuit and your first CMOS. So this structure where you build a structure with a PMOS with the PMOSs, and then over here with CMOSs that complement each other. This isn't very clear with this. There's better examples with ANDs and ORs and other structures. And I'll go through it in other videos, but this is a very basic explanation. Basically, you have PMOS, an implementation with PMOS, an implementation with NMOS, and you use them together to create a greater circuit. And you can kind of bootstrap that into bigger circuits. So the high level of all this, like why are we talking about any of this? Maybe you're just a layperson who's just kind of interested in circuits. The magic is that this action from a very high level of turning on a switch, um, and being able to feed that into other switches that can do similar things. You can do math pretty much. This is kind of an old idea. We're talking about von Neumann probably before that, but people figured out it's like, oh, like if you could just have electrical circuits that can turn on other circuits, that could actually do computations. And there's ways to chain it, to make adders, which is just you could subtract as well if you have negative numbers, and then once you can add, you can multiply, right? And if you can multiply, you can divide. Not to say that just multiplications and divisions are easy, but once you can do that, you can do a lot of computation. And there's probably more theory to this that I'm not aware of, or I'm not an expert on, that I'm not going to act like I know. But this is kind of how you start to build calculators. This is how you start to build computers. And of course, the big hype about it is like what are the limits of computation? And if you really care about computation, that's a whole other thing. But this is why we're learning about this. Like, okay, great, you can turn. I only bring this all up to say that. Okay, great, we can turn on switches. What does that mean? What does that do for us? It does a lot for us in the end. And of course, if you're here, I assume that you already have a need to know. But that's just kind of more like some reflection. So anyway, so this is like an inverter circuit. I explained to you PMOS, NMOS, and then ultimately CMOS, how to use a PMOS and NMOS in a circuit um, to actually keep chaining logic, which is we're using voltages to determine that. So maybe that's the other side I want to say, that with this, you can't really um, you can't really use logic off this. You could, but this is the CMOS. There's a lot of advantages, but maybe the biggest one is that there's a straightforward way to chain it. But basically, you're trying to either block the top, we'll say the top of the circuit here, or you're allowing it to get expelled here at the bottom. And that's a general strategy that we'll see later on when we talk about ands and ors. And if you're not familiar with Boolean logic, maybe we could talk about it at that point. So anyways, thanks for your time, everyone. And take care. See you guys.